Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Okay, good to go. And thanks for attending this course again. So today we will continue on the explanation on RISC. We haven't finished yet on our last lesson. So yeah, today we'll cover about characteristic of reduced instruction set architectures. Okay, so yeah, there are a variety of different approaches to reduce instruction set approaches have been taken, but certain characteristics are common. Okay, there are characteristics that are common. So these four. Okay, so one instruction per cycle, register operation, simple addressing modes, and simple instruction formats. Okay, the first characteristic is that one machine instruction per machine cycle. So what a machine cycle? A machine cycle is defined to be the time it takes to fetch two operands from registers, perform an ALU operation, store the result in a register. Okay, so RISC machine instructions should be no more complicated than and execute about as fast as micro instruction on CISC machines. And with simple one cycle instruction, there is little or no need for microcode, and the machine instruction can be hardwired. Okay. And second characteristic is that most operations should be register to register with only simple load and store operations that access memory. Okay, and this feature simplifies the instruction set and therefore the control unit. For example, RISC instruction set may include only one or two add instruction. Okay, the fax has 25 different add instruction. Another benefit of such an architecture for the second characteristic, it encourages the optimization of register use and frequently operand remains in high-speed storage. And the third characteristic is simple addressing mode. Okay, so although all RIC instruction is simple register addressing, several additional modes such as displacement, PC, relative may be included. The other more complex modes can be synthesized in software or simple software. And a common characteristic, the final one, is simple instruction formats. Okay, so here that we have, you see, uh, one or few formats, okay, are used. And with these, instruction length is fixed and aligned on word boundaries. Field locations, especially the opcodes, in here, are fixed. And this design feature has some benefits. With fixed fields, the opcode decoding and register operand accesses can occur simultaneously, and simplified formats simplify the control unit. Okay. Instruction fetching is optimized too because the word length units are fetched. Okay. And alignment on word boundary also means that single instruction doesn't cross page boundary. And then together, the characteristic can be assessed to determine the potential performance benefit on an RAC approach. That a certain amount of circumstantial evidence can be presented. First, more effective optimizing compilers can be developed. Okay? But we are dealing with more primitive instruction, and there are more opportunities for moving function out of the loop, reorganizing code for efficiency, maximizing register utilization, and so forth. And it is even possible to compute parts of complex instructions at compile time. And yeah, in most cases, this will all be known as compile time. I mean, time, the movement, the length of the string. Okay, and thus the compiler could produce an optimized sequence of primitive instruction for this function. Second point, which already noted before, is that most instructions generated by compiler are relatively simple anyway, and it will be reasonable know that a control unit built specifically for those instructions and using little even know microcode that could execute them faster than comparable CISC complex instruction set code. Okay. Then a third point here that is pointed out is that it relates to the use of instruction pipelining. RISC researchers feel that instruction pipeline technique can be applied much more efficiently with this instruction set. Okay. And the final point is that somewhat less significant that is that RISC processors are more responsive to interrupts because interrupts are checked between rather elementary operations. Okay. So, okay. Now we are discussing about CISC versus RISC. Okay, so yeah, we need to see here. RISC design may benefit from the inclusion of some CISC feature. Second is that CISC design may benefit from the inclusion of some RISC features, and the result is that more recent RISC design, notably the Pbcsc, are no longer pure RISC, and the more recent CISC design, notably the Pentium 2 and later Pentium models, do incorporate the RISC characteristic too. Okay, so here's typical classic RISC characteristic. Yeah, so they are maybe quite long. I want to read it by myself. Okay, it's about the instruction size, the number of data addressing modes, type of addressing, and operation. Okay, how the maximum number that use the MMU. Okay, and something like that. Okay. Now we'll skip to RISC pipelining, and this is also very important. Okay, so RISC pipelining. Okay, let's see from the first one, which is pipelining with regular instruction. Okay, so instruction pipelining is mostly used to enhance performance as has been outlined in the previous lesson. Okay, so for RISC architecture context, then you see that most instructions are registered to register, and an instruction cycle has the following two stages, which is instruction fetch and execute. Okay. For load and store operation, there are three stages that are required, which is instruction, fetch, execute, and memory. Okay. And let's see the description on the figure 13.6a. Okay, here's the okay. So we have sequential execution for the A, and later we have the two-stage pipelining timing, and later we have three-stage pipelining timing and four-stage pipelining timing. So what we can see from here is that even very simple pipelining can substantially improve performance. Okay, the two stages of the pipeline are an instruction fetch stage and execute memory stage to execute the instruction to the register to memory and memory to register operation. And thus, the instruction fetch the second instruction can be performed in parallel with the first part of the execute memory stage. Okay, but also we need to note that the execute memory stage of the second instruction must be delayed until the first instruction clears the second stage of the pipeline. Okay, this can yield up to twice the execution rate of the serial. And yeah, there are two problems outlined here. So first is that we assume that a single port memory is used and that only one memory access is possible per stage. And the second is a branch instruction interrupts the sequential flow of execution. Okay, and then later we also have three-stage pipeline timing. Okay. Okay, so the improvement is as much as a factor 3. Okay. So again, that branch instruction causes the speed up to fall short of the maximum possible. And if an instruction is an operand that is altered, then the preceding instruction, a delay is also required. And this can be accomplished by a no-op. Okay. And pipelining discussed so far work best if the three stages are on approximately equal duration. Okay. Therefore, equal duration. Okay. And even it's outlined here that we can do up to 4 instructions at a time. That we can do a potential speed up to a factor of 4. Okay. Then we'll see how to do optimization of pipelining scheme that we have taken. The first one is that we need to see about the delayed branch. Okay, so to compensate for the dependency, what dependencies? Yeah, the one that I outlined before. Okay, then we need to code reorganize. Okay, we need to code reorganize. Okay, first, let's see how to do branching instruction. That a delayed branch is to increase the efficiency of the pipeline. It is done by making use of branches that doesn't take effect until after execution of the following instruction, and the instruction location immediately following the branch, and it's referred to as the direction. Okay, so we have something called the normal branch. Also, we have something called the delay branch. And then we have something called the optimized delayed branch. Yeah, this is just the description. There's nothing that's going very important here, so I'll skip to delayed mode. Okay, so the next thing here is that we do delayed load. So actually this is some sort of syntactic tool that can be used on load instruction. So on load instruction, register that is to be targeted in load is then locked by the processor, and the processor then continues execution of the instruction stream until it reaches an instruction that requires that register, and at which point it idles until the load is complete. And if the compiler can rearrange the instructions so that it will be useful work that can be done while the load is still pipelining efficiently, and the efficiency can be increased. They have loop unrolling. Okay, so yeah, the unrolling can improve the performance by these three factors. Okay, first is that it reduces the loop overhead, then it increases the instruction parallelism by improving the pipeline performance, and it can improve the register, the caches, and the TLB locality. Okay, actually there are some kind of things highlighted here, but I don't think it's very important. Okay, this is very machine specific. Spark. Also, this is kind of okay. Let's see directly with this RIC versus CIC controversy. So yeah, there is a general trend for years in computer architecture organization that yes, which were increasing processor complexity and more instruction, more addressing modes, and more special register, and so on. So the RIC movement represents a fundamental break with the philosophy behind this trend. And yeah, the appearance of the RIC system and the publication of papers by its proponents installing the RIC virtues led to a reaction from those in front of the CIC architectures. And yeah, there are some work has been done on asserting the merits of the RIC approach. Okay, there are two categories here. There is outline. The first one is quantitative, that attempts to compare program size and the execution speed of the program, the RIC and CIC machines that use a comparable technology. And the second one is that the qualitative one, which examines the issues such as a high-level language support and the optimum use of the FLSI world estate. But there are several problems as outlined here for the attempting such comparisons between the RIC and the CIC related machines. I mean the related implementation. Okay. First, there is no pair of RIC and CIC machines that are comparable in life cycle cost, level of technology, the gate complexity, the sophistication of the compiler, the operating system support, and so on. The second one is that no definitive test set of the program exists. The third one, that it's very difficult to sort out hardware effects from effects due to the skill in compiler writing. And four is that most of the comparative analysis on the RIC has been done on toy machines rather than for the commercial product. So it's actually, yeah, not very fair. Okay, good. So let's see. Yeah, that yeah. Okay, you see this paragraph. So in more recent years, that the RIC versus CIC controversy has died down to a great extent, and this is because there has been a gradual convergence. Okay, so you see that we have gradual convergence of the techniques. And as chip densities and raw hardware speeds increase, the RIC system have become more complex. And at the same time, there is an effort to squeeze out the maximum performance. The CIC design have focused on issues tradition associated with the RIC, and then we have solved the problem so far. Okay, now let's see a new chapter. Let's see if it's in. Okay, now we have entered a new chapter, which is on the instruction level, parallelism, and superscalar processes. But maybe we will not go into that today. I will have another video on this chapter later. Okay, so first thing that we want to discuss today is that what is the difference between the superscalar versus the super pipeline, and what's the limitations that we'll discuss about the design issues. Okay, with what is instruction level parallelism and about machine parallelism. Also, we have what is instruction issue policy, that was just the renaming the machine parallelism, and yeah, so on, so on. Okay, but yeah, maybe we will not go into the example. Okay, this is a Pentium 4 and ARM Cortex A, and I think it's not the technology being used now. Okay, it has been kind of obsolete. Okay, but let's see the concept that is brought here. Okay, so let's analyze for the key concept. This is the summary of the chapter. So a superscalar processor is one in which the multiple independent instruction pipelines are used, and each pipeline consists of multiple stages so that each pipeline can handle multiple instructions at a time. Okay, so each pipeline consists of, the multiple pipelines introduce a new level of parallelism. Okay, so we have some called parallelism, which enable the multiple streams of instructions to be processed at a time. And a superscalar processor exploits what's known as the instruction level parallelism, which is actually the degree to which the instruction program can be executed in parallel. A superscalar processor typically fetches multiple instructions at a time and then attempts to find nearby instructions that are independent of one another and can therefore be executed in parallel. And if the input to one instruction depends on the output of a preceding instruction, then the latter instruction cannot complete execution at the same time or before the former instruction. And such dependencies have been identified, and the processor may issue incomplete instruction in order that differs from the original machine code. Okay, and there are many kind of things. Okay. Yeah. Okay. So this is the point. So a superscalar implementation of a processor architecture is one in which common instructions, integer and floating point arithmetic, loads, stores, and conditional branches that can be initiated simultaneously and executed independently. Okay. Yeah. The term superscalar itself is first coined in 1987, which refers to a machine that is designed to improve the performance of the execution of scalar instruction. Okay, so the bulk of the operation are on scalar quantities in most applications. And accordingly, that the superscalar approach represents the next step in the evolution of the high-performance general-purpose processor. Okay, so the essence of the superscalar approach is that the ability to execute the instruction independently and concurrently in different pipelines. Okay? So it can be further exploited by allowing the instructions to be executed in order different from the program order. So here, the figure that shows how a superscalar approach be done. Okay, you see, there are pipeline functional units here. Okay, so there are multiple functional units. Okay, each of which is implemented as a pipeline that support parallel execution of several instructions. Okay. So what is the difference between superscalar and super pipeline? Okay. So super pipelining, which is first coined in 1988, exploits the fact that many pipeline stages perform tasks that require less than half clock cycle, and thus a double internal clock speed allows the perform two tasks in one external clock cycle. Okay, so here's the figure. They show the comparison between two approach, which is the super pipeline one and super scalar. Okay, so the base is pipeline issues one instruction per clock cycle and can perform one pipeline stage per clock cycle. The pipeline itself has four stages, which are instruction fetch, and also it has operation decode, also operation execution, and the result write back. And this the execution stage is crosshatch for clarity. Okay, so next part, the B part, so a super pipeline implementation that is capable of performing two pipeline stages per clock cycle. Okay, whereas for the super scalar one, okay, it's capable of executing two instances of each stage in parallel. But here's the limitation. The superscalar approach depends on the ability to execute multiple instructions in parallel, and the term instruction level parallelism refers to the degree to which an average the instruction of a program can be executed in parallel. The combination of compiler-based optimization and hardware techniques can be used to maximize the instruction level parallelism. Okay, but here's the limitation that needs to be considered. Okay, related to parallelism. Okay, the first one is true data dependency, second is procedural dependency, third one is resource conflicts, the fourth is output dependency, and the fifth is anti-dependency. Okay, so first is true data dependency. Okay, actually the book provides us with the example, but I'll not go to explain the example. Okay, so what is actually true data dependency? Okay, you see, the second instruction can be fetched and decoded but cannot execute until the first instruction executes, and the reason is that the second instruction needs data that produced by the first instructions, and this situation is what called the true data dependency. Also a flow dependency, or sometimes they also call the term of write after read dependency. Yeah, so yeah, the previous figure shows the dependency of degree 2. Okay, so there must be some delay in here. Okay, so that is the important thing. Then we have procedural dependencies. Okay, what is procedural dependencies? It comes because we have what the mechanism of branch. Okay, so these branches sometimes will give us bring us problem. Okay, so the instructions following a branch, taken or not taken, have a procedural dependency on the branch that cannot be executed until the branch is executed. Okay, and it affects the scalar pipeline. So the consequence for a superscalar pipeline is more severe because of greater magnitude of opportunity, which is lost with each delay. And if a variable length instructions are used, then another sort of procedural dependency also arise. And because the length of any particular instruction is not known, then it must be at least partially decoded before the following instruction can be fetched. And this prevents the simultaneous fetching required in superscalar pipeline. Then we have resource conflict. Okay, this is the last one for the lesson today. So resource conflict is a competition of two or more instructions for the same result at the same time. Okay? The resources meant here may include memories, cache, bushes, register file ports, and the functional units like ALU. And in terms of the pipeline, that a resource conflict exhibits similar behavior to a data dependency, which is outlined at the first one. There are some differences here. For one thing, the resource conflicts can be overcome by the duplication of the resources, whereas a true data dependency actually cannot be eliminated. Also, when an operation takes a long time to complete, then the resource conflicts can be minimized by pipelining the appropriate functional units. Okay, so I think maybe that's the end for the lesson today. So I want to share a quote for you today. So Oprah Winfrey once said, "If you look at what you have in life, then you always have more." Okay, that's all today. And that's all our lesson for today. Thanks for watching. And here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https science with xyz.unux.com. Keep watching and be thoughtful. Goodbye.